Hello. There is no PowerPoint for this lesson 10. It's actually almost completely examples. I call this lesson Rearranging Formulas, which the goal there is then pretty straightforward. Students should be able to rearrange a formula that has multiple variables for a specified variable. Some people call this solving literal equations. And literal is the idea that it's full of letters, and then whatever you're solving for, they'll call the subject. But I don't usually talk about it that way. But I have seen it discussed that way, so I want you to at least have heard of it. A lot of the formulas we're going to use might look familiar from math itself or science. And so this is what your notes page should look like. And I've already loaded the examples here into Paint. And so what I recommend students do to get started is sort of look at the formula, look at what variable you're supposed to solve for, circle that variable, just that variable, and realize that everything's outside of the circle you're going to have to get rid of. So you can figure out how is it attached to the variable that's circled and then move it. Well, hopefully you can agree that pi r squared is being multiplied by h. And so if we want h by itself and we want to move or cancel all this and get it to the other side, well, to undo multiplication we use a division. And so this will be actually maybe one of the few times where you see me do a little bookkeeping, just because it's all variables. And I'm going to move potentially more than one thing at a time. Like in this case, I'd go ahead and for this volume of a cylinder formula, if I want to get h by itself, I would just go ahead and divide by pi r squared on both sides. And so these would cancel out completely to 1, and 1 times h is h. And you can't really do anything with what's over here. And so what you would have is the volume divided by pi r squared is equal to the height of the cylinder. That, by the way, is the area of the circular base, in case you're wondering. So if you take the volume of the cylinder and divide it by the area of the circular base, you should get the height. Alright, this next example is a linear equation, but instead of numbers for a, b, and c, it's actually just a, b, and c. And we just sort of want to solve this in general for x. And so let's see, we've got an a being multiplied by x and a b being added. And socks and shoes rule would say that you need to use inverse operations and cancel this addition by b first. See, we'll subtract b. So these will cancel out to 0. And you can't really do much with c minus b other than copy it. Now, still trying to solve for that x, and it's still a times x. So inverse operation to cancel this multiplication would be division. This division would, cancel to 1. 1 times x would be x. And so in this case we would have x equals c minus b over a. Okay, that's the first two. Let's take a look at the next two. Okay, standard form of a line, we're going to solve for y. It's ax plus by equals c. We want this y by itself. Everything else needs to be moved over to this side. Well, you would get rid of this addition before you get rid of the multiplication by b. So we're going to subtract ax on both sides of the equation. And so these would cancel out to 0, and 0 plus by would be by. And for reasons that might not be 100% clear right now, I'm going to write this as the opposite of AX plus C, because I want it to look a little bit more like what you're used to seeing. I'm going to write the X term in front. Well, now I need to solve for y, and it's b times y. So I'm going to divide by b. And those b's cancel to a 1, and so it'd be 1y. I could leave this way, but to make it look a little more like something you're used to seeing, I'm going to write it as the fraction opposite of a over b, x, plus c over b. And the point of doing that is so that I can remind you of y equals mx plus b. You hopefully remember from a previous math class, and you'll realize that this was standard form of a line. This is slope-intercept form. And so you might see a little bit about how these two forms are related. This m is kind of like the opposite of AB. This little b is like big C over big B. We'll be starting graphing before too long, so I want to go ahead and remind you of that. Alright, so now we have the Fahrenheit to Celsius temperature conversion. And right now it's in terms of F. And we want it to solve it so that it says C equals or equals C. And we have this fraction right here that's being multiplied by C, and then we have the addition. So we'll go ahead and do the subtraction first. Kind of undo our order of operations. We'll subtract 32 on each side, keep it balanced. Now to make it 100% clear here what I'm going to do. I'll switch to purple for a second. I don't like the 9/5. I don't like it because of the denominator. And so I multiply by 5, those will cancel out. But that means I need to be careful and make sure I distribute over here. So you end up with 5f. Now, 5 times 32. Well, 5 times 30 would be 150 because 5 times 3 is 15. 5 times 2 is 10. So 150 and 10 is 160. So minus 160 equals 9c. And then now that's attached by multiplication, so we can just divide. And 9 won't go evenly into either of these. And so we can either leave this alone. That's what I think I'll do in this case. 5f minus 160 divided by 9 equals degrees Celsius. So if you have a Fahrenheit temperature that you're interested in converting to Celsius, multiply it by 5, subtract 160, and divide by 9. Simple, right? Alright, let's look at a couple that are a little tougher. Here's the way gravity works mathematically, according to Sir Isaac Newton. It was kind of a big deal. The force of gravity is equal to a constant, this is just some number, g for gravity, times the product of the two masses involved. So if we were talking about the gravity between, I don't know, me and the Earth, my mass, Earth's mass. My mass, while not super tiny, is practically insignificant compared to the Earth. And then you would divide that by the radius squared, where the radius in this context is the distance between the centers of the objects. So between the center of me and the center of the Earth, which for purposes of people walking around on the Earth, that's just about the same as the radius of the Earth. You don't add too much to it. A couple extra feet doesn't really matter for gravity. But if we were talking about the Sun and the Earth, then you would be comparing the mass of the Sun to the Earth to the square of the distance between them. This is an example of what scientists call an inverse square law. In an inverse square law, the idea is that the power or force involved drops off at the square of the distance. And so that you would have a denominator with some sort of distance squared. This works for, off the top of my head, gravity and light intensity, and maybe something with springs, like Hooke's law or something. I don't remember for sure right now. I'd have to look that up, and I didn't yet. So here we go. We want to solve this for a radius, which is in the denominator. So I think I'll start by multiplying by the denominator, radius squared, just to get it out of the denominator. And I've got to remember that's now multiplication. So I want this radius by itself, and it's being multiplied by the force. There's also this exponent too, so we would get rid of multiplication before we get rid of an exponent. So we'll divide by force. Radius squared equals gravitational constant, product of masses, all over the force. Some of you might have been comfortable sort of almost skipping straight from the original formula to here, but I wanted to show it to you. And so now for sort of the thing that's new and different. We haven't really done a lot of this yet this year. What would get rid of this square? I've been hinting at it all along. What gets rid of a square? Well, if you think about Gesundheit, our mnemonic that we agreed upon for order of operations, you might have kind of figured out by now. If you ignore grouping symbols, I put a pair of operations on each level: exponents, radicals, multiplication, division, addition, subtraction. And each of these pairs are inverse operations. And so what the inverse operation for a exponent is going to be is a radical. So we do need to take the square root of both sides. And a square root of a square is just going to leave us r. I have to go back to blue. I'll leave us r. And there's a little bit more to all this, but for right now this will work. And this square root doesn't really simplify. So we get the square root of a not very nice looking fraction, where the numerator is the product of gravitational constant and the two masses, and the denominator is the force between them. So all I really wanted to do, honestly, with this problem was show you the square of a square root trick. Honestly, I want to go ahead and throw that in because we'll be needing that for too much longer. And then this one, we've got another trick, honestly, we're going to use here. We've got, oh, look at that. We've got L, rectangular prism surface area. We've got L in two different spots. What it is this formula is the surface area of a box, or the amount of wrapping paper it would take to cover the surface of the box. And so this is like length times width would be like, say, the front, and then the width times the height would be the sides, and then the length times the height would be like the front and the back, or something like that. And you got to double this because, you know, there's the two sides match, the front and the back match, the top and the bottom match. And so basically you've got the area 3 different rectangles and you double them all and add them together. So the problem is that creates 2 different copies of L. So we got to sort of sort this out and get this down to a single copy of L if we can. Well, I know a lot of you want to distribute. And you could go ahead and divide by 2, or you can go ahead and distribute. I bet so many of you would distribute, but I guess I better go ahead and do it that way just so you can see. So let's say you do decide to distribute the 2. 2LW plus 2WH plus 2LH. Now, remember, we want these L's by themselves. So this piece doesn't have an L at all, so and it's being added, so we can go ahead and subtract that. That we can handle. That minus didn't come out very clear. I'll just stick a little extra minus in front of it. So the left-hand side would be the area minus 2WH. And then this side would be 2LW plus 2LH. Oops, let me just undo that. We want, I did it again. Alright. We want these L's by themselves. And if they were just being added, we could subtract the other piece. If they were just being multiplied, we could divide. Problem is, it's kind of all together. And it turns out, remember how you distribute it up here? Well, you basically have to undistribute. These pieces both have L's. So here's a distributive problem. That I care about. I claim that if you distribute this L, it would go back to being the step above it. This is something you might remember from your previous algebra class called factoring, right? You factored out the common factor L. We talked about common factors this year, so you shouldn't be too terribly shocked to see this coming. Now what we have is, if you look at that, we've gone from having 2 L's to just 1, and it's being multiplied, so we can divide by 2W plus 2H, the whole quantity, on both sides, and we'll be down to just L. So we would have this not very pretty looking fraction equals L. And I think if I tried to squeeze that in there, it would just be a mess. So I'll be sneaky lazy and just sort of write that. Sorry. Technically that should be right here too, but I think it would just be a mess to try to squeeze it in. Alright. We got one last example here at the bottom of the page. And it's going to use that sort of similar idea. It's solved for x, and there's a bunch of other variables running around, and it looks like a pretty good Algebra 1 problem, except for the fact that the A, B, C, E, F, G are just letters instead of numbers. I mean, if these were numbers, this would be like one of the harder problems, maybe from lesson number 8, which was easier linear equations. And so now we're going to figure out how to do this. Solving an equation business when, you know, there are no numbers. And so we usually distribute first. So here we go. ABX minus AC plus E equals F of Fx minus g. Okay, now we've got an x there, an x there. So when we want the x's together, so let's subtract fx, which will cancel those out. So now we've got a bx minus fx minus ac plus e equals opposite of g, or negative g. Should be opposite of g if you want to get real technical. And let's see, we still have an x and another x. Okay, so we don't need these two pieces, that one's being subtracted, one's being added. So I think you can handle this. I'm going to add AC and subtract E, plus AC, subtract E. I'm going to do all that at once. Okay, so now we've got A bx minus fx equals, since AC is positive, and the only thing over there that's positive, I'll put it first. AC minus G minus E. I'm running out of space here. Now we have to use a trick like from that last example, where we've got the two terms that both involve x, and we've got to factor it out, or sort of like combine like terms. And okay, so we're going to have x times what? AB minus f equals what? AC minus G minus E. And then we've got the x by itself here times AB minus f, because if you distribute this, you go back in, and distributing is multiplying. And so I'm out of space, so you can't see it if I put it at the bottom, so I'll just write it right here in purple or something. What would x equal? Well, we would divide by this quantity. So here's our numerator, there's our denominator. The numerator would be AC minus G minus E all over a denominator of AB minus F. None of these things combine. Nothing cancels out till we know what the numbers A, B, C, G, E, F are. We can't really decide what this is. But if you pick numbers for A, B, C, E, F, G, put them in, and you've already done this, you could actually go straight to this and put the values in, turn the crank, and you'd have your answer. Okay, so this is the solution of any equation of that form right there. Alright, that's lesson 10, which is all about equation solving, but with no numbers for the most part. It's just moving the symbols around, following the rules of algebra. Hopefully you were able to follow that okay. If not, let's make sure we do a few extra in class or something. Alright, I will see you later, talk to you later. Good luck with this. Maybe go back and watch the last couple examples again, because they were a little tougher. Alright, thanks. See you next time. See you in class.